right, so my research was a doctoral set on casino games, specifically craps, and how intricately designed they are. Like, they're very careful when they set these games up because there's a lot of money at stake. So,
you want to make sure they win.
yes, a casino is a business, and as a business, they want to make money. And so, to do this, some businesses, they sell things. Casinos sell the chance to win big money because you play games with the famous games that you think of at a casino is like slot machines or poker or something. But other games that they have, blackjack, roulette, and craps are the more, the power is taken away from either the house or the player, and it's just pretty much luck of the draw. So the saying is the house always wins, because even though the house has no direct control over what the outcome of the game will be, these games are designed in such a way so that the odds are just barely balanced in favor of the house winning. So 51% of the time, the house will win. And so eventually, as thousands and thousands of players come through, they end up making any money they lose, they make back and make some more on top of that. So craps specifically, what is that? It's not the most famous of the games, but it's a die game. You have two 6-sided die, and it's easier to show you how it works. So you've got the two die, and you roll them, and we have a 2 and a 3. So that adds up. We look at the sum, we get 5. And this is the first roll. So if it's not a 7, it's not an 11. It's not a 2, 3, or a 12. So that means that we don't instantly win or lose the game. We get to keep going. So now, from here on, our goal is to roll another sum of 5. So if we roll again, I actually got 5, so I won. So that was fun. And so you would place a bet, and the bet is just whether or not you will win the game. You're not betting that a specific number will come up like in roulette. You're just betting whether or not you will win. So it's a win-lose scenario. We roll again on a second game, and we get 8. And so we would do the same thing. The 8 is the point, is what it's called. And you roll again to try and get that 8 later. If you roll something on subsequent roll, and I rolled a 10, so 10 is not 8, so I don't win. But it's also not 7, so I don't lose, so I just get to roll again. So on the first roll, if you roll a 7 or an 11, you instantly win the game. If you roll a 2, a 3, or a 12, you instantly lose the game. And then on later rolls, if you do have a point marked because you didn't instantly win, if you don't roll the point, you roll again until you get the point, or you get a 7 and then you lose. And because this is a 2-die game, if you look at the distribution of possible sums, 7 is the most common. So that's why they have 7 marked as an instant loss later, because it's the most likely to occur. So looking at craps, I decided I wanted to look into how well designed the game is. And I did this by varying the odds of winning and varying the number of die that win. So 7 and 11 win on the first roll. So there's only 2 possible sums that will win on the first one. But I thought, what if we have 3 die sums that win that add up to the same probability total of getting any of the 3 but there's 3 now, not just 2. Does that change it, or does that stay the same? Also, doing the same thing using die, seeing and changing the number of sums will affect that. And then also wanted to see if we could look at other possible setups of the game. So not just a 2-die game, not we could throw in a third die and see how that changes the game. Or we could change it to be using, instead of 6-sided die, we could use 10-sided die, or 4-sided die, 8-sided die, or what have you, and see how does that affect it. So, how are we going to be able to actually look at this, right? There's a lot of different possible combinations because we've got a bunch of die going on here, and you roll them again and again. So how do you represent all of that information? And then how do you take all of those possible states and the probabilities of each of those and abstract it to a probability of winning the game as a whole? And so we use Markov chains for that. So what is a Markov chain? Really, a Markov chain is just a graph. Each node in the graph is a state, and each edge in the graph is a possible transition between the states. So the important thing to note about a Markov chain is that the states and the transitions are the same every time. So no matter what you have done in the previous turn, your state graph will look the exact same on the next turn. So no choices that you make will change the probabilities in the Markov chain. So each edge has a possible transition probability. So if we want to represent this in a more useful manner, we can take it and put it as a table. So if you look, the probability of transitioning from state A back to state A is 75%, so that's this right here. And then from, say, B to C is 0.375, so that's right here. And so we've just changed it, instead of being in a graph form, we just represented it as a adjacency matrix. And so if we put this into its matrix, we can use that and multiply the matrix by itself multiple times to find the probability of being in any given state after a given number of turns. So when we set n to 2, so on our second turn, if we started out in state A, there's a almost 70% probability that we'll still be in state A on the second turn. Whereas after 9 turns, we only have a 2/3 chance of being in state A still. And so as you multiply it by itself again and again, some matrices like this one will converge to a specific probability. So that will tell us overall, when we abstract it out, these are the odds of being here. So going from state B to state B again, just in general, after however many turns, we'll probably have 14.8% chance of being in B still, if we start. So this is the Markov chain for craps. Standard game. We have a 2/9 chance of winning on the first turn, because that's what the odds of getting those sums are. The 7 and 11 add up to 2/9, and the 2, 3, or 12 add up to 1/9. And so the rest of these states then are the other possible odds of getting that number, particular number, marked as the point. So all of these add up to 1 when you add up the entire row. And then we have our winning state. So if we're in our winning state, we have 100% probability of being in the winning state the next round, because we won, so we're not going to keep playing. And if we lose, same situation, we've got 100% probability of staying in the losing state. And then on subsequent rolls, we have the same number here. We've got the same probability of rolling the point on the subsequent roll as we did on the first roll. So there's only 1/9 chance of rolling a 5 on the first roll. And the next time we roll the die, it's the same probability of rolling a 5. Because nothing changes, we're just rolling the same die again. And because if we roll a 7, we lose on subsequent rolls, all of these have the same probability of losing later. That's the only way to lose, is rolling a 7. So this right here then is the probability of having to re-roll the die. So this is the probability of winning, this is the probability of losing, and this is the probability of re-rolling. So we have a very good chance of having to go multiple turns before we either win or lose the game. And so when we take this matrix and we raise it to a bigger power, this one is 100, then we get to see from our starting state a probability of either winning or losing the game. So we can see that it's balanced just so that there's a 50.7% chance that the house will win the game. So these are just some more matrices that instead of the standard one, these are set up slightly differently. We've got different combinations of die that will win or lose. So you can see that we've got the same 2 9s, 1 9, and 16.7 on all of these for our winning, losing, and losing probabilities. So we don't change the probability of winning or losing, but what we do change are these here, 3, 5, 7, 8, 9, 10, and 5, 6, 7, 8, 9. So we change all of the different die that can be marked as the point, is what's happening. And so you can see when we take these out, we get very different odds of the house winning. So we get possibly 50.1% chance, or 47.9%, or 51.7. So some general results from all of these matrices that we built. The losing combination on the second roll doesn't matter, only the sum. So what that means is, if we look here, we've got our initial and for winning and losing, and they're set up 7, 11, and 2, 3, 12. So this top row is the standard game here, with 50.7% chance of winning. And the row right below it, it has the same initial conditions, but we change what die will make us lose on our subsequent rolls. So instead of only 7 being losing, we change it so that 2, 3, 11, and 12 will make us lose. And that adds up to the same probability of losing, and it gave us the same probability of the house winning. So no matter what we do on our subsequent rolls, which ones we choose, as long as they add up to the same probability, it won't affect our game. And this is because, if you think about it, all of these have to be taken from the die that were marked as either winning or losing instantly at the beginning. We can't have, say, a 4 in our here, because 4 is a possibility to be marked as the point. So we can't have something that can be the point that will also lose us the game later. So none of these then would appear in these columns, because the columns are only the ones that can be marked as the point. So we can't have the losing one in this column. So the only thing it affects is this number right here. So it won't actually change our matrix at all. The Markov chain will look the exact same Markov graph between these two top rows even though they're set up differently, when we build the Markov graph, they look the same. The other thing that we have as a result, the less die that cause an instant loss, the more likely the house is to win. So looking here, we have 7, 11, 2, 3, 12. That will cause an instant loss. So we've got 5. And then if we go down here, we've got 7, 11, 2, 4. So we only have 4 die now that will cause an instant loss. And our probability of the house winning has gone from 50.7 up to 51.7. So now there are more possible die that can be marked as the point, and the odds of the house winning have increased. And the same with this row here. Now we only have 3 die that can instant lose, so we have added another possible point. And our odds of winning have gone up to 53%. So if you think about it, it's because of when you roll a die, the more options you have to be marked as the point, the less likely you are to roll that same number later. So although it seems like it should be a good thing to have more possibilities of winning, it's actually worse for you because you're less likely to roll it later. Especially because if they all add up to the same probabilities here, the 8 and 4, 3 and 6, since they all add up to the same probabilities, the die that we're giving the player as a possibility to win with, it's a possibility to be marked as the point, actually have individually less probability of being rolled. So we're taking away the die that are more likely to win them and giving them back worse die.
So counterintuitive.
Yeah. And the other thing, the more sums that instantly end the game, the more likely that the house will lose. So that would be this one. We've got 7, 11, 2, 3, 12, and here we have 6, 11, 12, 2, 4. And so we've got 5 that will instantly end the game, and 5 that will instantly end the game. And the odds are very close, not quite the same. Really, really close though. 50.7 and 50.1. But if we change it so that 7, 11, 2, 3, 12, and then 4, 10, 11, 2, 3, 12, our odds of winning have decreased all the way to 47.9%. So now it's not even balanced in the house's favor. The player's probably going to win. Because there's more chances of, on the first roll, you're going to end up losing the game or winning the game, so it just ends right there. And so, really the way that the house wins in craps is by dragging the game out longer and longer. So the more rolls you have, the less likely you are to win. So, now looking at the 3-dice version of the game. All of those 3 things that we just talked about still hold true in the 3-die version. But even more noticeably, we have the more die that win, the less likely that the house will win itself. So this is the one that I set up as the baseline. We've got these are the same odds. These fractions evaluate to the same probability, the 2/9 and 1/9, and 1/6. So we've got all the same probabilities as the 2-die game, but we have substantially more possible combinations of possible sums of the die. So we've got all the way up to 18 now. So we've got a 3rd die added in. So in this baseline I set up, the house has 52.7% chance of winning. And that's quite clearly 2% higher chance of winning than the standard version of craps with 2 die. So when we add in another die, the odds are that the house is going to win because, like we just said, we've given them more possibilities, more possible sums to be marked as the point. And so the game will be dragged out even longer, and the house will probably win. So we can see through the second row the same situation as we showed with the 2-die game. The combination of our second losing on the subsequent rolls, the combination, as long as it adds up to the same sum, is irrelevant. It'll give us the same odds of winning. And here we can see that when we have less instant winning, we have, or losing, instant ending the game on the first roll, we have better odds of the house winning. And we've given more here, so when we have more odds of instant ending the game on the first roll, we have less odds of the house winning. So the patterns hold for 3 die, but the ratios, it's important to note, do not hold, because adding in the extra die has added in more point possibilities, which has made it harder for the player to win. So 52.7% is not very good odds for the player to win, even in a casino. So that's why the game is balanced so well, because 50.7% is pretty much not noticeable in terms of the player. You know, they'll feel like they're winning quite a bit. I won just now in our demonstration right off the bat. So it seems really good for that. And it's important to note, 7, 11, 2, 3, 12, 7, there's only 4 numbers you have to keep track of. It's pretty simple rules for the game. Whereas if you look at this other one, that 50.1% chance, you got 6, 11, 12, 2, 4, 6, 12, adding in another die, so there's more to keep track of, and the odds aren't balanced all that well in favor of the casino anyway, so they don't go for that one. And then we've got a 50.4 here, but there's more die added in still, so it keeps getting more complicated. So in terms of balancing the simpleness of the game with the odds of the house winning, you can see why they went with the rule set that they did. And so if we then look at the different types of die, rather than just the 6-sided die, we can see these patterns that form. The more sides on the die, the more likely the house will win. Because just like adding in another die gave us more possible points, same thing happens when you add more sides to the die. You get a wider variety of points. So if we have 2 4-sided die, there's only a 42.1% chance that the house will win. So that's pretty unbalanced towards the player. And if we actually change which, you can see we only have 2 that will instantly end the game, and then on our second one we've got 4 that will instantly end the game, and the odds of the house winning just fall drastically. We get down to 35.8% chance of the house winning, which is awful for them. So it's pretty obvious why they don't use a 4-sided die. If we add in a third one, we can see that the odds of the house winning do rise, but not quite enough. It's still below 50%. It's down to 46. But if we go, the next standard die after 4 and then 6 would be 8. And so if we look at that one, suddenly the odds of the house winning shoot up to 56.3% chance. So 4 sides is way too low, and 8 sides is too high. Even if we try to put in more instant win lose, we still only get down to 52.5. So the best balanced die of them all is in fact the 6-sided die, which is why they go for that, I'm sure. Plus they're the easiest to find, and everyone's used to them anyways. And then if we look at 10-sided die, it goes up to 57.4%. So that's just way out there. And yeah, not only is it the more sides, but the more die you add in, the more likely that the house will win. And the more sums that is in the game, the less likely that the house will win. So all of these patterns hold for not just our 2 6-sided die, but for any combination of any number of sides. We can see that the more die we add in, the more likely that the house will win. So basically, as a conclusion, craps was very carefully set up when casinos started to offer it. The house does always win with the 50.7% chance, but it's just right so that you don't really notice. So people keep coming back and playing again and again, and eventually they will lose. And so, like we said, the rules are balanced just right so that it's easy to understand and play, but it's also just the right odds for the house to offer it and make a profit. And so, really the takeaway from this is it's the choice of how many die will instantly win or lose the game that matter more than what the odds of rolling those possible sums are. Because in all of these chains that I showed you, the sums of the probabilities were the same. They were all the same ratio, 1/9, 2/9, 1/6, or for other non-6-sided die, they were a quarter and eighth. And so, if you hold all of those ratios the same and just vary how many die it is, you can get an actually much bigger effect than if you change the ratio of what the odds are of winning. So, that's the takeaway from this. Are there any questions?
I was thinking,